Introduction. Generative AI agents represent a significant advancement over standard language models, designed as applications to achieve specific goals by perceiving their environment and using tools to act upon it. Unlike traditional models, agents synthesize reasoning, logic, and access to external information to perform tasks autonomously, often without explicit step-by-step instructions. The architecture of an agent is built on three pillars. Model, the core language model, LM, that serves as the agent's decision-making brain. This can range from a general-purpose model to one that is highly specialized or fine-tuned for a specific task. Tools, these are the instruments that connect the agent to the outside world, allowing it to interact with external data and services. Tools can be extensions that link to APIs, functions, self-contained code for specific tasks, or data stores that provide access to current information, keeping the agent's responses grounded and relevant. Orchestration layer. This is the cyclical process that governs how the agent reasons, plans, and acts. It manages the agent's memory and state using prompt engineering frameworks and reasoning techniques like chain of thought to guide its interaction with the environment and effectively complete tasks. This document serves as an advanced guide for developers focusing on agent evaluation methods and the practical application of Google's agent products to solve complex, real-world problems. AgentOps. While it's relatively easy to create a proof of concept with generative AI, ensuring high quality and reliability for production is a major challenge. AgentOps is the solution, defined as a subcategory of GenAOps, generative AI operations, focused on the efficient operationalization of AI agents. AgentOps inherits best practices from established fields like DevOps and MLOps. However, it introduces specific components tailored to agents. Tool management, handling both internal and external tools the agent uses. Agent brain prompt, managing the agent's core instructions, including its goal, profile, and operational guidelines. Orchestration and memory, overseeing the agent's reasoning process and its ability to remember past interactions. Task decomposition, breaking down complex goals into smaller, manageable tasks. Like its predecessors, AgentOps relies on a cycle of measurement and optimization. It requires robust version control, automated deployments, testing, logging, and security. The core idea is to use metrics to understand what the system is doing, measure outcomes, and incrementally improve performance. Agent success metrics. Metrics are fundamental to building, monitoring, and improving agents. While high-level business metrics like revenue or user engagement are the ultimate North Star, agent-specific metrics are needed to guide development. Key metrics for agent success include goal completion rate. Since agents are designed to accomplish goals, this is a primary indicator of success. Critical task and interaction success. Goals are often composed of smaller, critical tasks or user interactions. Each of these should be instrumented and measured independently to pinpoint where the agent succeeds or fails. Application telemetry. Standard software metrics like latency and error rates are crucial for understanding the agent's performance and reliability. Human feedback. A simple thumbs up/down or a user feedback form provides invaluable qualitative data on where the agent performs well and where it needs improvement. This feedback can come from end users, QA testers, or domain experts. Detailed traces. For debugging, it's essential to have detailed logs, traces, of the agent's internal workings. These traces record every step of the agent's reasoning process, allowing developers to dig into the details when a problem arises. Agent evaluation. To move an agent from a prototype to a production-ready system, a robust and automated evaluation framework is essential. Unlike evaluating a simple generative model, which focuses only on the final output, agent evaluation requires assessing the entire decision-making process. This process can be broken down into 3 core components. 1. Assessing agent capabilities. Evaluating the agent's fundamental abilities, such as understanding instructions and reasoning logically. 2. Evaluating trajectory and tool use. Analyzing the sequence of steps and the choice of tools the agent uses to arrive at a solution. 3. Evaluating the final response. Assessing the quality, relevance, and correctness of the agent's final output. Automated testing is far more efficient than manual testing in the long run, providing deeper insights into agent behavior and building confidence in the system. Assessing agent capabilities. Before building a custom evaluation, developers can leverage publicly available benchmarks to understand the core capabilities and limitations of the models and components they are using. There are public benchmarks for most fundamental agent skills, such as tool calling. Benchmarks like the Berkeley Function Calling Leaderboard, BFCL, assess an agent's ability to correctly select and use tools. Planning and reasoning. Benchmarks like PlanBench evaluate an agent's ability to plan across different domains. End-to-end performance. Holistic benchmarks like AgentBench attempt to capture performance across multiple realistic scenarios. While these public benchmarks are a valuable starting point for identifying potential pitfalls, they may not perfectly reflect a specific use case. Therefore, organizations often develop their own use case-specific evaluation frameworks. Evaluating trajectory and tool use. An agent typically performs several actions before providing a final response to the user. This path of actions is known as a trajectory. Comparing the agent's actual trajectory to an expected or ideal trajectory is a powerful technique for debugging, identifying errors, and spotting inefficiencies. There are several automated methods for evaluating trajectories based on a ground truth or reference trajectory. Exact match, the most rigid metric requiring the agent's trajectory to perfectly mirror the reference trajectory. In-order match, a more flexible metric that checks if the agent completes all the core steps in the correct order but allows for additional unpenalized actions. Any order match. This metric disregards order entirely and simply checks if the agent performed all the necessary actions regardless of sequence. Precision and recall. These metrics measure the relevance and completeness of the agent's tool calls. Precision asks how many of the agent's actions were actually necessary, while recall asks how many of the necessary actions the agent actually performed. Single tool use. This helps determine if an agent has learned to use a specific important tool. A key limitation of this approach is the need to have a reference trajectory, which must be created beforehand. Evaluating the final response. Ultimately, an agent's success is determined by whether it achieves its goals. This is assessed by evaluating its final response. This can be automated using an auto-rater, which is another LLM that acts as a judge. The auto-rater is given the user's input, the agent's response, and a set of predefined success criteria. It then assesses the response against these criteria, mirroring a human evaluation. For this to work effectively, the evaluation criteria must be defined with extreme precision, as they form the basis of the entire assessment. While many libraries provide predefined criteria, they should be treated as a starting point and tailored to the specific definition of a good outcome for the use case. Human-in-the-loop evaluation. Automated evaluation methods are powerful but have limitations. They can struggle with subjective qualities and may not capture the full context of a problem. Therefore, it is crucial to incorporate a human-in-the-loop approach. This is especially valuable for tasks requiring subjective judgment, nuance, or creative problem-solving. Key benefits of human evaluation include Subjectivity. Humans can evaluate qualities that are difficult to quantify, like creativity and common sense. Contextual understanding. Human evaluators can consider the broader implications of an agent's actions. Iterative improvement. Human feedback provides direct insights for refining the agent's behavior. Evaluating the evaluator. Human feedback can be used to calibrate and validate the automated autorators, ensuring they align with human preferences. Methods for implementing this include direct scoring by experts, comparing an agent's performance to previous versions, and conducting user studies where participants interact with the agent and provide feedback. More about agent evaluation. The field of agent evaluation is complex and rapidly evolving. Key challenges include the difficulty of finding or creating good evaluation data and the limitations of using LLMs as judges, which may prioritize final outcomes over the agent's reasoning process. Future trends in agent evaluation are moving towards process-based evaluation that focuses on understanding the agent's reasoning, AI-assisted evaluation methods for greater scalability, a stronger focus on real-world application contexts, and the development of new standardized benchmarks to allow for objective comparisons between different agents. Continually refining these evaluation methods is essential for ensuring that AI agents are developed and deployed responsibly and ethically. Multiple agents and their evaluation. The next evolution in AI systems is the move towards multi-agent architectures, where multiple specialized agents collaborate to achieve complex objectives. A multi-agent system is like a team of experts, each with a unique role and potentially using a different LLM, all working together to solve a problem. This approach offers several advantages over a single-agent system. Enhanced accuracy. Agents can cross-check each other's work. Improved efficiency. Agents can work in parallel to speed up task completion. Better handling of complex tasks. Large tasks can be broken down into smaller subtasks, each handled by a specialist. Increased scalability and fault tolerance. The system can be easily scaled by adding more agents, and if one agent fails, others can take over. Within these systems, agents can be categorized by their function, such as planner agents, breaking down objectives, retriever agents, fetching data, execution agents, performing actions, and evaluator agents, validating responses. Multi-agent design patterns and their business impact. To design effective multi-agent systems, several design patterns have emerged that define how agents interact and delegate tasks. Common patterns include sequential. Agents work in an assembly line fashion, with the output of one agent becoming the input for the next. Hierarchical. A manager agent coordinates the workflow and delegates tasks to worker agents. Collaborative. Agents work together, sharing information and resources to achieve a common goal. Competitive. Agents may compete with each other to achieve the best outcome, with the final decider choosing the best response. The choice of pattern depends on the specific application. These patterns help businesses reduce operational bottlenecks, improve knowledge retrieval, and enhance the reliability of automation. Important components of agents. The architecture of LLM-based agents, especially in multi-agent systems, consists of several critical components. Interaction wrapper. The interface managing communication between the agent and its environment. Memory management. Includes short-term working memory and long-term storage for learned patterns. It also involves reflection, where the agent decides what to move from short-term to long-term memory. Cognitive functionality. The reasoning engine, often using frameworks like chain of thought or React to decompose tasks and self-correct. Tool integration. A subsystem that allows agents to discover and use external tools. Flow or routing. Governs connections with other agents, facilitating delegation or handoffs. Feedback loops. Mechanisms for continuous learning by processing outcomes to refine future decisions. Agent communication. A standardized protocol for agents to share messages, tasks, and knowledge, which becomes even more critical for remote or asynchronous communication. Agent and tool registry. A system for discovering, registering, and selecting the right tool or agent from a mesh based on their capabilities and performance metrics. Challenges in multi-agent systems. Despite their advantages, multi-agent systems present several challenges. Task communication and allocation. Efficiently dividing tasks and communicating them in a structured way can be difficult. Coordinating reasoning. Getting agents to effectively debate and reason together requires sophisticated coordination. Managing context. Keeping track of all the information and conversations between multiple agents can be overwhelming. Time and cost. Multi-agent interactions can be computationally expensive, leading to higher costs and user latency. Complexity. While individual agents may be simpler, the overall system becomes more complex to manage, similar to a microservices architecture. Multi-agent evaluation. Evaluating a multi-agent system is a natural extension of evaluating a single agent. The same core principles apply. Business metrics remain the North Star, and trajectories and final responses are still the best focus for automated evaluation. However, a trajectory in a multi-agent system may involve actions from several or all agents. This allows for evaluation at multiple levels. Each agent can be evaluated in isolation, and the system can be evaluated as a whole. Unique questions for multi-agent evaluation include cooperation and coordination. How well do agents work together? Planning and task assignment. Did the system create the right plan, and did the agents stick to it? Agent utilization. Did the system select the right agent for the job and use it effectively, e.g., as a tool, via delegation, or by transferring the user? Scalability. Does the system's quality improve as more agents are added? Agentic RAG, a critical evolution in retrieval-augmented generation. A significant advancement in multi-agent architectures is Agentic Retrieval-Augmented Generation, Agentic RAG. Traditional RAG is often a static, one-shot process of retrieving information and feeding it to an LLM. Agentic RAG transforms this by introducing autonomous retrieval agents that actively and iteratively refine their search. These agents enhance retrieval by context-aware query expansion, generating multiple refined queries to retrieve more comprehensive results. Multi-step reasoning, decomposing complex queries into smaller steps and retrieving information sequentially. Adaptive source selection, dynamically choosing the best knowledge sources based on context. Validation and correction, using evaluator agents to cross-check retrieved knowledge for errors before it's used in the final response. This approach significantly improves response accuracy, explainability, and adaptability, making it crucial for complex knowledge retrieval tasks. Better search, better RAG. Before implementing a complex agentic RAG system, it is often more valuable to first optimize the underlying search engine. Improving search results directly improves the quality of any RAG implementation. Key techniques for improving search performance include better parsing and chunking, using advanced parsers that can handle complex document layouts and semantic chunkers that keep related information together. Adding metadata, enriching chunks with metadata like keywords, dates, and categories allows for more powerful filtering and ranking. Fine-tuning embedding models, customizing the embedding model to better represent the specific domain of the data. Using a faster vector database. Upgrading to a faster vector search can improve both speed and accuracy. Using a ranker. A second-stage ranker can reorder the initial search results from a vector search to ensure the most relevant items are at the top. Implementing grounding checks. A final safeguard to ensure that every phrase in the generated response can be cited back to a retrieved chunk. Agents in the enterprise. In 2025, agents are set to become integral to the enterprise, assisting employees with specific tasks or running autonomously in the background to perform automation. Two main types of agents are emerging. 1. Assistants. Interactive agents that take a task from a user, execute it, and return a result. These can be general purpose or highly specialized. 2. Automation agents. Agents that run in the background, monitoring systems or data for events, and then acting on them by fixing problems or notifying the right people. This will shift the role of knowledge workers from being doers to being managers of agents. They will assign tasks to multiple agents, monitor their execution, and provide approvals, orchestrating a virtual team of AI agents through new user interfaces. Google Agentspace, NotebookLM Enterprise, Google Agentspace Enterprise. Google offers a suite of products to facilitate this new era of enterprise agents. Google Agentspace, a platform that harnesses Gemini's reasoning and Google's search power to provide employees with access to enterprise information and automate complex workflows. It prioritizes trust and security with features like SSO, RBAC, and granular access controls. NotebookLM Enterprise, a research and learning tool designed to help users synthesize complex information from various source documents. The enterprise version brings these capabilities to businesses with enhanced security and features like AI-generated audio summaries. Google Agentspace Enterprise provides employees with a unified, company-branded search agent that serves as the definitive source of enterprise information. It connects to various third-party applications and allows for the creation of custom AI agents tailored to specific business functions, complete with tools for development, deployment, and management. From agents to contractors. The current way of defining agents, with a simple goal, instructions, and tools, is often underspecified, making it difficult to move from prototype to production. A proposed evolution is to treat agents as contract-adhering agents or contractors. The key idea is to formalize the interaction using a contract, which would precisely define deliverables and specifications, what makes the outcome acceptable and how to verify it. Scope, what the agent is and is not responsible for. Cost and duration, expected resource usage and timeline. Reporting and feedback, how the agent should provide progress updates. This contract would be negotiable, allowing the agent to request clarification on ambiguities or suggest changes. This more formal approach aims to improve reliability and trust, especially for complex or high-stakes tasks. The ability to generate subcontracts would also allow a contractor to decompose a large task into smaller, manageable pieces. Automotive A. Real-world use of multi-agent architecture. The automotive industry provides a compelling real-world example of a multi-agent architecture in action. An in-car conversational AI system can be composed of several specialized agents. Conversational navigation agent for finding locations and guiding the driver. Conversational media search agent for finding and playing music, podcasts, etc. Message composition agent for drafting and sending messages. Car manual agent for answering questions about the vehicle's features using RAG. General knowledge agent for answering general factual questions. These specialized agents are combined using various design patterns. Hierarchical pattern, a central orchestrator agent routes queries to the appropriate specialist. Diamond pattern, a variation where the response from a specialized agent passes through a central rephraser agent to adjust its tone and style before being delivered to the user. Peer-to-peer pattern. Agents can hand off queries to one another if they recognize that the initial routing was incorrect, creating a more resilient system. Collaborative pattern. Multiple agents contribute different aspects to a single query, e.g., technical specs, practical advice, and a response mixer agent combines their inputs into one comprehensive answer. Adaptive loop pattern. An agent iteratively refines its approach, e.g., reformulating a search query, until it achieves a satisfactory result. This multi-agent approach provides specialization, efficiency, higher quality responses, and resilience, e.g., critical on-device functions continue to work even if cloud connectivity is lost. Key takeaways for developers. 1. AgentOps is essential. Adopt best practices for tool management, orchestration, memory, and task decomposition. 2. Metrics drive improvement. Use a combination of business KPIs, granular task metrics, and human feedback. 3. Automated evaluation is key. Evaluate agent capabilities, trajectory, and final responses using automated frameworks. 4. Human in the loop is crucial. Use human evaluation to handle subjectivity and calibrate automated systems. 5. Multi-agent systems offer advantages. Use specialized agents in collaborative patterns for complex tasks. 6. Agentic RAG improves relevance. Go beyond traditional RAG with agents that actively refine and evaluate searches. 7. Search optimization is foundational to RAG. Improve your underlying search engine first. 8. Agent and tool registries are important. Manage your growing ecosystem of agents and tools with a registry. 9. Security is paramount. Prioritize security with platforms that offer built-in controls. 10. Efficient use of developer cycles. Consider using platforms and products as alternatives to building everything from scratch. Future directions. Research and development are focused on advanced evaluation methods, better multi-agent coordination, real-world adaptation, explainability, long-term memory, and more formal agent communication protocols such as the agent as contractor model. The future of AI is agentic, and developers are encouraged to start building the next generation of intelligent applications using the tools and techniques discussed. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.